Hi guys, good morning. In this video, we're going to see the third lecture of our bar graph series. In this, we're going to see the graph representation. Okay, you're about to start working on graph, right? But how will you represent that graph? Because graph is just nodes and vertices, as I told you in the last video. It's just nodes and vertices. So you need to represent that in the form of code, right? How to write in the form of code? We're gonna see that in this video. So a quick recap of graph. So basically we have this graph and the question is how to store this graph. What to store is a question. Graph is represented by this vertex and this edge, which means every graph has an identity which is corresponding to its vertex and its edge, which means edge is just which connects to vertices. Okay, so to just represent this graph, we have four ways to represent it, or basically in four forms we write our graph codes. First one and the second most common one is create a 2D array. It is also called as an adjacency matrix. Now what I mean to say is that if you have these two nodes, let's say 0 and 1, you know one thing, okay, 0 and 1 are connected and they are connected by an edge. 0 and 1 are connected. We have some nodes, we have these nodes, and we know, okay, 0 and 1 is connected. While we also know that 0 and 3 are not connected. So why not to just store this condition? Okay, whosoever is connected, I'll just assign a value 1 to it, which means if 0 and 1 is connected, I just have a value 1. While 0 and 3 are not connected, so it is just empty, which means it is having a value 0. So basically, these represents nodes, these also represents nodes, and the values here, it represents the connection. So as you can easily see that these represent our connection inside the matrix. So if we go on to next value, which means 0 and 2, they are also connected. So 0 and 2 are connected via an edge called this. 1 and 3 are also connected. 1 and 3 are also connected via this edge. So I just marked a 1 here. Similarly, I can just mark for everyone. 1 and 3 are connected. So 1 is connected to 3 and also 3 is connected to 1. So as you can see, I just marked colorfully. What the word is that you can easily see that, okay, which edge is connected and how they are being connected. While in the case of a directed graph, which means you only have the edge in one direction, as you can see, from 0 to 2 I have an edge, while from 2 to 0 I don't have an edge. So from 0 to 2 I have an edge, I marked a 1. Node to node I have an edge, which means the value of that matrix, I have that particular edge. Okay, I just marked a 1. While 2 to 0 is not there, right? Because it's just directed edge. So from 2 to 0 I have nothing. And as you can see, I just marked a 1. While in this case, it was an unweighted graph. While as I told in the last video also, we can also have a weighted graph. In the case of a weighted graph, we can just assign some value, let's say 6. So from 0 to 1, instead of placing a 1 right here, from 0 to 1, I can place a 6. This 6 will represent, yeah, we have an edge and its weight is 6. Because it's a non-zero value, so it means we have an edge. And it has some value, which means, okay, what's the value? It's 6. 6 is the weight of that particular edge between 0 and 1. It is the second most common way to represent a graph by just nodes and matrix represent, okay, if we have an edge or not. But why I said it's the second most common way? It's because it has a few disadvantages and also a few advantages, but these are much more. Although not saying that we don't use it, we use it, but in very rare cases where it is actually required. And how to know it's actually required? Let's see. If we want to know that there exists an edge between node U and node V, if you want to know there exists an edge, then we can just find it in O(1), because we just need to go in this matrix and check, okay, what is the value between node U and node V. If we have a 1 or if we have a non-zero value for a weighted graph, then we can just say, okay, we have an edge. So in O(1), I can just check, okay, if that edge is present between node U and node V. It's a very good thing. So whensoever we are about to say, okay, just Aryan, I just want something in which I can just let know in O of 1. I want to get, okay, if an edge between node U and node V is present, so I'll just use a matrix. While it has a few disadvantages, or I should say many. Firstly, we have to store all edges, which means I have to keep record, okay, 3 and 0 is connected or not, 3 and 1 is connected or not, 3 and 2 is connected or not, 3 and 3 is connected or not. So basically, I know it's not connected. Still, I have to store an empty location for it, so as to make sure, okay, ultimately I should know, okay, if there's an edge between node U and node V or not. So it is just using a lot of memory for us. And also, if we want to find the neighbors of a graph, we need to iterate over the whole entire row. Let's say if at this place I wanted to know who is the neighbor of 2. So only I know 1 is there. Neighbor of 2 is only 1, right? Because it's a directed edge. Or let's say this example. Neighbor of this particular 1 is what? Neighbor of this 1 is 1, 2 and 3. So to actually find all the neighbors, I have to iterate here. Although it was not having a neighbor here, but still I have to iterate it. While in the case of 3, let's say I want to find its neighbor, I have to iterate. I know it's 1 only. It's only 1 neighbor, but still I have to iterate here also, and here also. Which means to find the neighbor, I have to iterate the whole array and not only the neighbors. Wasn't it useful that I could have only iterated on the neighbors itself? Why to iterate on the whole array itself? Right? Thus, it's also a big disadvantage. So as I said, it's also second most commonly used. So let's see how it is being written. In the left, in this portion, you can see the C++ code, the corresponding exact same code you can see in the right. For this case, I just showed one is how you can just write in the actual code, in the actual program, actual example, actual exam, how you write the code. And it is, I just hard coded some values. The corresponding code for this C++ is below in Java, exactly same. Like here I just use scanner, here I just use a cn, else exactly the same code. So you can just see this simultaneously. I have also have the notes in the description down below, exactly what you are seeing right now on your screen. I've written down the exact same code for you to just have that notes with you and just go on with me. Now, firstly, I just grab that input. N is the number of nodes, M is the number of edges in that graph. I make that graph I represent by GR, and then it represents N. So the N is the number of columns, N is the number of rows and N is the number of columns. Why? Because N nodes and N columns. Thus, I have this graph with me. Now, I just go, see, same. I just grab that input N and M. I just make the graph as a matrix of N cross N. Then I just go on, grab every edge. I'm going on to every edge. My edges are M. I go on to every edge. I just grab, okay, what is the U and V? Every edge is from a node to a node, right? From a node to a node. Node U to node V. I just grab that and I just marked, okay, from U to V, I have an edge. From V to U, also I have an edge, because it's an undirected graph. While in the case of it had been a directed graph, so I just had it, okay, from U to V I have an edge, so I just marked it here. While if it says, okay, only V to U you have an edge, so I just have removed this particular thing and only V to U you have an edge. Same goes for here also. I just grabbed my U and V, which means for an edge. Okay, what's its U, what's its V? As it's an undirected graph, so I just marked both U to V as 1 and also V to U as 1. While if it had been a weighted graph, so you would have put a value whatsoever is the weight. But I will not confuse you. You just have to remember about the unweighted graph. And same, the exact same thing, how the weights are being assigned from U to V, from edge 0 to edge 1. Sorry, from node U0 to node 1, you are assigning a particular value which is 1, saying, okay, it has a weight. Node 0 to node 1, I have an edge with a weight 1, and weight 1 is just nothing but, and if everyone has a weight same, we say 1, so it's an undirected edge. Same goes for here, same goes for here. And the exact same thing, I just made a graph as a 2D matrix. Now, it was the adjacency matrix. Next, not so common, but usually you see in the programs how the input is being given to you. Not sure if it's a graph or not, but it will be given like this. Okay, you have the vertices, you have the edges. So it just says, okay, you have the vertices. Next is that you have the vertices, you have the edges. Edges, as you can see, between 0 and 1 you have an edge, so I just write 0 1 1 0. Between 1 and 3 I have an edge, I just write 1 3 3 1. Between 1 and 2 I have an edge, so 2 1 1 2. Between 0 and 2 I have an edge, so 0 2 2 0. Thus I can easily represent my graph by this vertices and by this edges. As I said, a graph has one identity, and that is its vertices and its edges. You just have to make sure that you provide that. Here we have the vertices in the form of a matrix indexes and edges as the value of the matrix cell. Here we have the vertices in the form of a list and the edges also in the form of a list, where it represents, okay, these all edges are present. While in the case of a directed graph, it's just that one direction will be there. 0 to 1 is there, not 1 to 0. So I just only have 0 to 1. I only have 1 to 3. I only have a 2 to 1. I only have a 0 to 2. And the vertices are for sure there. As simple as that. Next, and the most common one, the most important one, the most superior one is adjacency list. I'm not saying it's always used. I'm saying it's most commonly used. Why? It's because how it is being made, it is memory efficient. It can bring out the neighbors in only whatsoever neighbors are possible. So we just only use this. Adjacency matrix is also used, I'm again saying, but in special cases where we just have to find, okay, if this edge is present between two nodes in O of 1 or something we want to optimize related to that. That's the reason. Now, let's see how this special thing works. So basically in this, as I said, we want a node, we want, okay, the edge, we want all the vertices, we want the edges. So if I can for sure know, okay, 0 has one edge to 1, one edge it has to 2. I just know this. And I also know, okay, I have earlier stored all the nodes. I only want to store only those nodes which are the neighbor of 0. So I'll think of something, okay, for 0, let's store only its neighbors. For 0, I stored only its neighbors, which is 1 and 2. For 1, I stored only its neighbors, which is 0, 2 and 3. For 2, I stored only its neighbors, which is 0 and 1. For 3, I stored only its neighbors, which is 1. You saw what happened. It's also a list. It's also a list. So a list, one element is pointing to another list. Nothing but a list of list or a vector of vector. Understood? I will have every node and I will just point that particular node. I'll just have every node and I say, okay, my node 0 is mapped to my node 1. My node 0 has my neighbor as node 2. So a node and all its neighbors will be here. With this help, what will happen is, firstly, let's see with the directed graph. With 0, I can only have 1 and 2. So I just have that. With 1, I only have 3. I have that. With 2, I only have 1. So I have that. With 3, I have nothing. So it's just empty. Now, what happened here is I am only storing the nodes that are required to me. What are required to me? I'm only requiring the neighbors of a node. Because for me, see, for me, if I want to traverse a graph, if I want to go in the graph, I just want to know what are my children's, what I am to go to. What I am to go to, so I want to know, okay, what are my neighbors? My neighbors and children both are same. So I just go on to those neighbors. So I just want to know the information of my neighbors, that set. Thus, it is the best algorithm or the best method to find the neighbors of the graph. Thus, and mostly we just want to go on to neighbors in the graph itself. We just traverse in the graph, and when traverse we just are moving toward neighbors. Okay, we just move to neighbor. So as it is the most efficient representation to actually move to the neighbors, because it just takes O of neighbor time. If I have a one neighbor, it will take O of 1 time to go or like it will take just one iteration to go. If I have 8 neighbors, so it will take 8 iteration to go. If I have n neighbors, so it will take n iterations to go. So it will only take about how many neighbors are there, only that particular time. Now every edge here is only being counted twice. Thus I can say my memory, because see, I'm just storing from 0 to 1, I'm storing from 1 to 0, right? So my memory is nothing but 2 into number of edges, because every edge is being counted twice. And also, what if that I have no edge, which means my graph is something as whole separate nodes, because one node, it's also a graph, right? As I showed you in the first video itself, sorry, second video itself, that it is a graph, although they are not connected to each other, but still it's a graph. So I have this memory of O of 2 into E plus N for an undirected graph. While in the case of our adjacency matrix, you saw we have a memory of O of N squared. That's pretty large. Here it's nothing but O of 2 into E plus N. And for directed graph, as we have only one direction, so only one edge, just O of E plus N for directed graph. The code, see it pretty carefully. Exactly same thing. C++ code is here. Exactly corresponding Java code is here. I'll explain both. And here is the hard-coded code, where we hard-coded some values to actually see how it is working. See, firstly, I just grabbed the values of N and M. I just inputted N. N is the number of nodes, M is the number of edges. Then I just make my graph. Graph was nothing. For every node, I just know in my graph I have N nodes. So for every node, I just need to store a vector, which means for every node, okay, what all list of neighbors are possible. It will just give me this thing. For this vector, what all neighbors are possible. Thus, I'll have this graph, which means it will show for every node, and this particular vector part, it will give me, okay, for that particular node, graph of I, where I, let's say 0, 1, 2, which means node 0, node 1, node 2, what all neighbors are there. So I just go on to my graph, which means I just go on to every edge. I just grab that node U and node V, because I know for sure that node U and node V are connected by an edge. So node U's neighbor is V, node V's neighbor is U. Node U's, which means if I have a node U and node V, so I just push in V in the node U's neighbor, because see, this vector is nothing but neighbor. This vector is nothing but neighbor. So node U's neighbor is V, node V's neighbor is U. So I just push in and I'm just good to go. Same goes for Java. It's nothing but I just have, instead of a vector, I just have a list of integers of this graph. Now, what will happen is every of this particular element will actually point to another array list. It is the list of integer and it will point to another array list. Same as what we did in C++. It was a array and every array element was pointing to a vector. That's it. Then I just go on to every of this edge. I just grab that edge. I just pointed my U. My U's neighbor is V, so I just added in my array list, and my V's neighbor is U, so I just added the same in my array list of. Thus, I can just easily get, and same I just hard coded that I just get that, and I just hard coded the same thing here. Firstly, I just made my particular graph exactly the same how we made here, and here instead of just passing U and V, I just pass the hard-coded values of U and V. U is here, V is here. Edge between U and V. U, V. Here also U, V. Here also U, V. Same as what we saw in the Java code below. So I hope that you guys got it. Last but not least, it's a pretty, like you will actually see this in the graph. Other people teach it in the graph, but actually you don't need to make a graph out of this matrix, which means it is called an implicit graph. What happens is this, we are having a 2D array matrix, and we need to find, let's say, connected components, or basically it's just a 2D array. It's not a graph, which means if I say, okay, if I have a 1 here, I'm not saying that, okay, 0 1 2 3 4 0 1 2 3. So I'm not saying, if I have a 1 here, I'm not saying that my 2 and my node 0 are connected. I'm not saying that. I'm just saying by this particular graph is that this particular node is connected with the above node, the right node, the bottom node, and the left node, if there is the left node, if there is above node, if there is a right node, if there is a down node. So this particular matrix, it's an implicit graph which it represents, okay, my node right here is connected with the above node, right node, below node, or left node. For example, the node right here, exactly right here, is connected with this node, this node, this node, and this node. So my neighbor of this node is nothing but the above node, right node, left node, and down node. So earlier my neighbors were nothing but, I just marked, okay, it's a node. But here my neighbors are nothing but the cells around me. So it's also a graph. It's called an implicit graph. You will see, I'll just make sure, I'll just have some questions with it. So, but you will see this by using like some algorithms, like finding the connected components. So basically in this, you will just find what is the size of this island, how big is this island, how maximum I can go in this island. You will all see this. But in this, that, okay, how the graph is being made, ultimately we don't have to make a graph out of it. But ultimately it is a graph. How it is a graph? Because every cell is connected by its up, left, right, down. I hope that you guys got all the 4 representations of graph. Mostly we will use adjacency list. And yeah, I hope that you guys liked it. If you liked it, and check it out. Goodbye, take care.